Okay, first I'd like to apologize for missing lecture last night, but hopefully we can get through most of the material and get you set up for your exam next week. So this is chapter 7. It's got the homework listed up there. It's split up into the individual types of questions that you might end up seeing when looking at this material. One of the things that we forgot to talk about, or I forgot to mention earlier this week, was we're looking at mechanisms, and resonance and mechanisms are going to come into play when dealing with this material. So ultimately it's all about the motion of electrons, which is kind of what's highlighted at the bottom of this. So what we're concerned about is how we move those electrons, and those are always going to move from a source of electrons to some place that lacks them or is attracting them. So it's almost always a negative to positive motion. Be very, very, very careful that you never actually move atoms with the arrows. You're only moving the electrons around. In both cases, both resonance and mechanisms, you find a source of electrons. A good source would be either lone pairs or pi bonds, and you'll move those electrons towards a chosen atom, or in the case of resonance, to a bond. You'll check to verify your octet satisfied in either case. In the case of resonance, if the octet is exceeded, then you can break a pi bond by moving the electrons away from said atom. In the case of a mechanism, we won't break, or you could break pi bonds, but what we're going to end up doing is breaking our easiest bond first, okay? Which could very well be a pi bond, but it might also be a sigma bond. In the case of a mechanism, we're allowed to break sigma bonds because we're making and breaking new sigma bonds. That's the goal of a mechanism. Okay? So remember that when you're going through and trying to push through a lot of these mechanisms and overall reactions. I mentioned that we've got some new parts or classifications that we can put on individual reagents. The biggest, or the two big new ones, are down at the bottom: nucleophiles and electrophiles. Okay? So we're going to be coming back and referring to things based on their nucleophilic ability or their electrophilic ability. Very, very similar to Lewis acids and bases. Just kind of be aware that those extra definitions are going to show up and you need to be able to use them. And we introduced a whole bunch of new terms when we looked at the alkyl halides, particularly in their reactivity. So we've got our substrate, which is ultimately where our reactivity is coming from. So we're looking at the alkyl halide itself. For the most part, when we're looking at our substrate, we're more concerned about the alkyl portion, and in particular, the atom from where the leaving group is attached. Your leaving group, being the next piece, is going to be the atom or atoms that take the electrons away from our substrate. So these electrons in that bond ultimately need to go towards our leaving group. And since we made a big deal about drawing where our electrons go, we can draw our bond. We're taking those electrons and we're moving them towards the leaving group. So your leaving group is something that is typically electronegative because it wants to attract those electrons. Further, it can be something, and ultimately it needs to be able to stabilize those electrons. Okay, so you can go back and look at those slides if you don't remember that. Your nucleophile, so here's our introduction of a new term. Our nucleophile is going to end up being an electron source that's going to come in and stabilize that carbon, okay, our substrate. As the leaving group leaves, our substrate loses electrons, so our nucleophile has to come in and somehow stabilize that loss of electrons by donating its own electrons. Okay? And then the last thing that we could evaluate would be the solvent. We're going to spend a lot less time looking at the solvent because it usually plays a more complex role than we really want to deal with this semester. But you will see the solvent and how it goes through and either interacts with our nucleophile or with our substrate / leaving group. Okay, so it plays kind of a complex role in between each of those. Actually, before we go on, typically when we look at an individual reaction, we would expect that, or we would predict, sorry, a little distracted here, we would typically see our reagent shown first, then followed by some compound that we're reacting with, typically above the arrow but not always, and then below the arrow, again, we typically see the solvent specified if the solvent plays a major role in the reaction. If it doesn't, sometimes we'll ignore it. Okay, so let's see if we can continue on. So our nucleophiles, I made some edits to our slide. The primary edit change, or the primary change that you should notice, would be our first rule. First rule, we need to donate electrons. We have to have donatable electrons. So if you look over the quiz, one of the questions had you compare CH4, I don't really have a lot of space to draw on here, but CH4 versus NH3. Okay. And that's intentional, or that pair was intentionally chosen because if we look at our second rule, oops, I didn't change the numbering very well here. If we look at our second rule, we would say negatively charged. Neither of these are negatively charged. And we can move to our third rule, which is nucleophilicy. And we'd say the lower the electronegativity, the more nucleophilic. Well, that would suggest CH4. Okay, except we have to go in sequence of our rules. We have to have donatable electrons. Okay, remember one of those simplifications way back at the beginning of the semester? I said sometimes on nitrogen, oxygen, or the halogens will imply lone pairs. There's a lone pair on that NH3. CH4 has no lone pairs. So while CH4 or carbon may be lower in electronegativity, it doesn't have any donatable electrons. So the nucleophilic group, or the more nucleophilic molecule, would end up being NH3. Okay, and if we wanted to look at the nucleophilic atom, we'd be referring to the nitrogen itself. Okay, so make sure when you go through and apply rules for nucleophiles that you're applying these sequentially. Start with donatable electrons, then move to looking for negatively charged, then nucleophilicity, or sorry, electronegativity. Size effects we won't really see in the lecture. That's largely solvent dependent and gets a bit more complex than I think I really want to deal with you guys for this semester. The last rule on here is actually going to become kind of important for us. Shouldn't highlight that in green because it's not a solvent effect. That last rule, steric hindrance, is going to come into play when we look at our elimination reactions, okay, which I think we'll get to in this discussion. Okay. So continuing on, we looked at the details of the SN1 mechanism, and one of our primary issues was cation stability. Okay, it's probably the most important aspect of our SN1 reaction. We have to form a stable carbocation. Okay, and the thing that makes each of these cations unstable is that positive charge. Whoops, let's try that again. The thing that makes each of these unstable is the positive charge. So we can evaluate how do we stabilize that positive charge. We need to bring in electrons, and what we can do is evaluate the atoms attached in each case, and we can start to see that in the case of these types of cations, or sp3-ish cations, we get more electrons. So we went through and we said we had 12 supporting electrons here, whereas if we go all the way up to the top with our zero area cation, we really only have 3 supporting electrons. Okay, so our tertiary cation is more stable because there's more electrons nearby to help kind of pseudo-stabilize it. There are other ways to stabilize cations. Okay, in this case what we're looking at is just the location or the proximity of electrons being nearby, but we aren't actually moving electrons towards it. Is there a case where we can actually shift electrons towards a positive charge? Well, there's a reason we started off the lecture with resonance and mechanisms. Depending on the structure, you might actually be able to stabilize a cation by physically moving electrons towards that positive charge in what we would refer to as a resonance structure. Okay, so be aware of that when you're looking through your individual reactions. When we move into chapter 5, we'll talk again about the stability of your carbanions, okay, or your carbon anions, but it's not going to play a huge role for this section of the material right now, so we won't worry too much about that. Okay. This kind of summarizes the detail of your SN1 reaction. Sort of goes through, well, it shows the mechanism fairly well. Okay, so the first step in our mechanism is the leaving group leaves, and you can see that with our arrow, our curved arrow showing the electrons in the bond between our substrate and our leaving group going towards the leaving group. This generates an sp2 hybridized carbon. Okay, so that carbon in the middle only has 3 electron groups. Okay, so what I ended up trying to do here was, instead of drawing it in a planar fashion, which you might be used to for an sp2 carbon, okay, I went through and turned it. Let me redraw that so we can get a better view on it. So what I did was rotate about this bond until the blue bond here is coming out at you, hence we get the wedge. If that blue bond is wedged, what happens to, let's go ahead and call it the green bond, that's now going to be aimed away from you. The p orbital must be perpendicular to those sigma bonds, try and get as far away from them as possible, and that's why we rotate it, because otherwise if I drew the p orbital in on this, okay, it's not particularly easy to see where it is. It's the one coming in and out of the plane. So when we do this rotation, we can now draw it a lot cleaner as shown up there. Okay. The reason this becomes important is that that positive charge is now both above and below the plane of the molecule, which means the nucleophile, our source of electrons, I forget what color, I think we've been using red for our nucleophile. Our electron source can either come in and stabilize the positive charge from the top or from the bottom. Okay? If you go through and look at an individual reaction, that means if we started with stereochemistry, we're going to lose it in our product, quote unquote lose it, because we'll end up with both the R and the S enantiomers around that position. Okay? So our product would end up being optically inactive. Very, very tricky. You won't see a lot of questions on it, but you can expect to see something about that. Okay? When it comes to the details of our reaction, we want a substrate that generates a stable carbocation. Okay? And I'm going to keep saying a stable carbocation. In the SN1 reaction, our unimolecular reaction, we need a stable carbocation. Okay? That positive charge, we have to do this first step before the substitution reaction can occur. Okay? And if the positive charge is never formed, can never go through to form the final product. Okay? So we need to form a stable carbocation. When it comes to the leaving group, it has to be a good leaving group. Okay? So we're looking at halogens, neutral species, things that have a lot of resonance. Okay? You can go through and go back to the last lecture to look at leaving group, good leaving groups. The nucleophile, as far as we're concerned in the SN1 reaction, isn't really all that important. The first step of the reaction was the most critical, okay? And in that first step of the reaction, there's no leaving group. Take a look at our starting material. There's nothing there. There's no nucleophile. So we don't really care about the nucleophile. As long as we have a source of electrons or any nucleophile present, we're going to see the substitution reaction occur. Okay, so it doesn't need to be a strong nucleophile. We'll come back to what a strong nucleophile is when we look at the SN2 reaction. As far as the solvent goes, it needs to be polar protic. Okay, I said we weren't going to talk a whole lot about this, but let's evaluate what's happening with our solvent. Okay, because that's what this slide is supposed to help show. If we have a polar protic solvent, okay, we've got a solvent then that has a very positive hydrogen. Okay, so we got the partially positive hydrogen. How can we get that hydrogen to be partially positive? Well, it needs to be bound to something that is willing to take the electrons away. What kind of thing would take the electrons away? Good call. Anything electronegative. Our most typical example would be something like an oxygen. Depending on what we're looking for, we could say we've got water as a polar protic solvent, maybe methanol or ethanol. Any kind of alcohol would also act as a polar protic solvent. Okay, well, why is this important? Okay, well, if we've got a protic solvent, yes, we have that partial positive on the hydrogen, but then we also have that partial negative on the oxygen. Okay, again, so why is that important? What did we say at the very beginning of this slide? Okay, we said that we must have a stable cation. The cation must be stable. So let's go back and take a look at our cation. How can we stabilize a carbocation? Okay, positive charge, stabilize positive charge. We need electrons. What did our solvent just supply? Electrons. Okay, so the solvent can be useful to help stabilize that carbocation. The partial positive of our hydrogen can also be used to help stabilize the leaving group. It's that intermittent stabilization that facilitates and helps the SN1 reaction along. Okay, so it becomes incredibly important to have a polar protic solvent. Okay, so again, go back to the slides that were posted for Monday's lecture, and make sure that you can look at a solvent and decide if it's protic or not. Okay, we don't really care about the polar part, because if it's protic, it's polar, period. So, real quickly, what does protic mean? We have a hydrogen bonding solvent. Okay, so a hydrogen bound to oxygen, nitrogen, oxygen or nitrogen. Okay, so those are kind of your bulk details of the SN1 reaction, kind of overall. We'll come back and look at yet another summary in a little bit after we finish our SN2 reaction. Okay. So when we look at the SN2 reaction, it's always a bit hard to try and put all the information for each of these reactions down on a single slide, but the SN2 is a little bit nice because it's all happening in a single step. So if we go back and take a look at this SN2 mechanism, what's happening? Our nucleophile, which in this case is going to be our OH minus because it's donating electrons. We know it's donating because we can see the arrow aiming towards our carbon. Okay. Attacks our substrate, our carbon, while the leaving group leaves. Okay, and we can see that with the arrow going from the carbon bromine bond towards the bromine. Okay. We technically don't have this thing in the middle. I'm going to erase that X in a second, and it goes straight over to our products. Okay. So, big things to point out here. Number one, we're getting a backside attack. Okay. When the nucleophile comes in, it has to come in as far away from the leaving group as possible. Remember, as the leaving group leaves, it's leaving with a bunch of electrons. Take a look at the product. You get Br minus with a negative charge. Our nucleophile came in with a negative charge. Okay, so if the nucleophile came in anywhere close to our leaving group, our OH minus say came in from this side, or attempted to come in from this side, it would butt into that bromine or the bromide leaving group, and it would bounce right back out. No substitution would occur. Okay, so our nucleophile must always come in from the back side of that bond. Okay, that can be better shown, and this is where our stereochemistry will come into play, in a transition state. There's a couple things that signify that it's a transition state. The first of which is that we're looking at the brackets around it. The second of which is that you see this double dagger symbol on the far right. Okay, that's to imply that this is what's happening as the reaction occurs. It doesn't physically exist. Okay, it just doesn't physically exist. Okay, and the phrase that you'll hear with this is that an SN2 reaction will typically results in an inversion of configuration. And our configurations are ultimately referring to R and S stereochemistry. Okay, and you can also hear that as a Walden inversion, which isn't super important. Okay, and that's because as the leaving group comes in, our nucleophile comes in, it pushes out the leaving group out the other end. Okay, And you'll notice that our nucleophile, keep calling it a leaving group, our nucleophile has a high priority. It's something that has to have partial negative charge, so it's typically coming in as a high priority element. Okay, well, what's our leaving group? Our leaving group is also typically a high priority. So what we end up doing is trading a high priority element across our carbon. So it leaves from one side and it comes in from the other, which means we see a switch in our configuration. Okay, so just to prove that, let's go through and test our configurations. So let's go back to our starting material. Okay, and let's pretend that our nucleophile hasn't come in and attacked yet. And what we're going to do is assign chirality to this. So we've got bromine, carbon, carbon, and hydrogen. Bromine has our highest atomic number, so we'll assign it a 1. Our hydrogen has the lowest, so it's 4. Okay, between the next two carbons, that one gets a little bit tricky. So when we go through and evaluate carbon versus carbon, no difference. So we can move to the atoms attached. I see 2 hydrogens attached and technically a carbon. In the other case, I've got 3 hydrogens. Okay, so carbon trumps the hydrogen. So if we're going to assign our priorities, sorry, I got to clean that up a little bit, we would assign 2 here and 3 here. Okay. Hopefully that model quiz that I made you go through and work on gets you comfortable with this, and you would be able to see that in the rotation of doing this, we are actually rotating not clockwise but counterclockwise. Yes. And we have the S configuration. Okay. Remember, we have to assign by rotating that 4, our lowest priority, away from us, which means we have to do a rotation. I'm going to leave that for you to do and confirm that I'm right, and hopefully I am right, but we'll find out here in a second. Okay. If we go over to our product now and try and assign configurations here, we'll still get 1, 4, 2, and 3. When we do our rotation here, okay, we kind of see that's our connection of arrows, but again, our lowest priority isn't aimed directly away from us. So we'd have to rotate it away from us, and in the process of doing so, what we'd end up finding is that we are rotating in a clockwise fashion. Okay, and we end up with R. So what happened? We switched from an S configuration to an R configuration in the process of this reaction. So we inverted our configuration. Okay? I think a lot of you are probably going to have questions on why I was able to do that RS thing. So instead of just skipping it and making you do it on your own, let me go through and do it with the starting material. Whoops, sorry, I meant to erase. So what I am suggesting doing with that, okay, let's erase the arrows connecting it to. Okay. Because the lowest priority isn't aimed correctly, what I'm going to do is rotate about my carbon-bromine bond to get the hydrogen aimed away, so the carbon and the bromine are still in the same plane. Okay, and as I do my rotation backwards, the hydrogen will now be aimed away. Our CH3 will be aimed at us, and then our ethyl, our CH2, CH3 will be aimed up. Okay, if we go through and again, number 1, 2, 3. Which direction are we rotating? Counterclockwise, S. Hey, look at that. Even a clock can be right every so often. Okay, hopefully that's kind of clear enough. So we'll go ahead and continue on. Okay, so the details of our SN2 reaction, when we're looking at our substrate. Okay, remember we said backside attack was what was necessary for this reaction to occur. Okay, our nucleophile has to come in from the backside of our substrate. So if we take a look at the backside of our substrate, we want that backside to have the least amount of electrons possible. Why? Well, what happens with our nucleophile? What is our nucleophile? It's a negative charge. That negative charge has to come in through the backside. If the backside has a bunch of electrons around it, what's going to happen? It's going to repel out and we don't see the reaction. Oof, that was supposed to be an arrow going away. Let's try that again. It will repel out and we don't get the reaction occurring. So when we look at our substrates, we can say smaller is better. Okay, we went through a couple classifications with the SN1. We said tertiary was better. Well, tertiary is really large, so we're looking at a well, let's go ahead and do our zero area. Zero area will react faster than our primary, faster than our secondary. The tertiary substrate has so much carbon electron bulk in the backside that we don't see the tertiary react. Okay? So when we're looking for our substrates, zero area, primary, and secondary are all valid substrate structures for our SN2. Our leaving group should still be a good leaving group. Halides are really good leaving groups as long as it's not fluoride. So your chloride, bromide, and iodide are all great leaving groups. So you can stick with those. The next complication here is that when we look at our overall reaction, okay, we need that good leaving group and we need a sterically unhindered substrate, but we also need a nucleophile that is strong enough to do that attack, okay, to force the bromide to leave. Okay? So in the case of this reaction, or the SN2 reaction, we need a strong nucleophile. It must be good. Okay? It must be a good nucleophile. Okay, so what were the rules for it being a good nucleophile? Well, the first and foremost was that we had to have donatable electrons. So that's great. That's the bare minimum requirement. Okay? But what's going to make it a strong nucleophile? Okay, well, the big red flag there is negative charge. Okay? If we have negative charge, typically looking at a strong nucleophile. Okay? You may not always see the negative charge. It may be hidden as something. Okay? So let's do a couple. Well, we've got one example already written up there. We've got OH minus. Okay, you can see that minus charge written in the upper right-hand corner. Okay, so that would be a red flag that we're looking at an SN2 reaction. Okay, we've got that negative charge. But what if it had been written as NaOH? Okay, well, NaOH is a neutral compound. Is that a strong nucleophile? Okay, well, instead of panning and saying, okay, well, there's no charge, it must not be a nucleophile, let's actually evaluate the linkage or the bond between our sodium and our hydroxide. Sorry, I just kind of gave it away. The sodium and the oxygen. What kind of bond do we have there? Well, that's a metal and a nonmetal. So an ionic bond. If it's ionic, what do we actually have? That's right, we have ions. We've got Na plus and OH minus. So why on earth would I show the Na plus? Because when we're running an individual reaction, we need a counter ion to stabilize our nucleophile. Okay, so we're never going to see just a straight nucleophile floating around on its own. It needs to be stabilized by something, even if it is only weakly stabilized, and that's the role of the sodium ion. When it comes to the exam, I will try my best to not include metals and just show you the nucleophile. I can't promise that, though. When it comes to your homework will almost always show the metal cation there to stabilize your nucleophile. Okay, so way back when I said knowing all your bonds and forces was going to be really, really important, this is one of the cases where it's important. You need to remember what's happening with an ionic bond and why you can ignore certain aspects of an individual structure. Okay. Last thing to evaluate is the solvent. Okay, and well, we might be able to squeeze it in here. Okay, so we really have to evaluate the four possible things. We've got polar, nonpolar, protic, and aprotic. We have to still be polar. We can't shift to a nonpolar solvent. And the reason comes down to our nucleophile and our leaving group. Both of those are ionic or charged. We need to stabilize those charges. Okay? We have to somehow, in the case of the beginning part, we have to get the nucleophile near our relatively nonpolar substrate. The only way to do that is to have a polar solvent that dissolves everything. It must dissolve everything. Okay? So it has to still be polar so that it can get the nucleophile into solution so that it can react with our substrate. So we must still be polar. The next part is deciding protic versus aprotic. Well, we have the answer here. It's aprotic. Okay, so what we'll do in this case, or at least what I find the easiest way to do this, is to actually go back to looking at the negative. Why not be protic? Okay, so let's clean up some of our reactions so we can see it a little bit better. If it's a protic solvent, what did we say we had? That's right, protic solvents, we had that partial positive hydrogen, okay, bound to our electronegative element. Okay, and we'll use methanol in this case. When we looked at the SN1 reaction, it was that partially negative oxygen that was really, really helpful. Okay, oxygen or nitrogen, because that could stabilize the carbocation. Okay, so that's great if we have a carbocation. Okay, that's for the SN1 reaction. Let's go through and look at our SN2 reaction. Where is the carbocation? Okay, kind of an obnoxious question because it isn't there. We don't have a carbocation. Okay, so that partial negative, even though it's present in this case, really isn't all that important to us. Okay, so let's see what happens with the partial positive of our hydrogen. Do we have something that could coordinate to a partial positive charge? Okay, for instance, do we have something that's partially negative that could interact with a partial positive? What did we say we needed for our nucleophile? It had to be strong, which meant negative charge. What does a negative charge pair up with? A positive charge. What happens in a protic solvent? Our partial positive protic solvent coordinates to our nucleophile. Okay, what does that do to the negative charge? It makes it less negative. If it's less negative, it becomes less of a good nucleophile. Well, what's our primary call for an SN2 reaction? We must have a strong nucleophile for the reaction to work. Which means if I use a polar protic solvent, I destroy my nucleophile. If there's no nucleophile, I can't get the SN2 reaction. Okay? So while I need a polar solvent to dissolve everything, it should not be so polar that I weaken my nucleophile strength. Okay? So that's why we have to have a polar aprotic solvent. Okay? So that's kind of the reasoning behind that. So for examples of aprotic solvents, or polar aprotic solvents, you can go back again to the slides from the last lecture and see what possible examples there are for that. I can list off a bunch of acronyms or terms for you. You can get THF, DMSO is a good classic one. Acetone is another common one. Okay, so you can look up those structures and evaluate. Oh yes, they are polar and they are also aprotic. Okay, so those are typical red flags for SN2 reactions. Okay, so I know that was a lot of information crammed into now at this point only 35 minutes. Okay, so it's going to take a little bit of practice digesting and working problems. This is where the homework comes in handy. Okay. The next thing we can do is again try and separate all this information and kind of tabulate it as neatly as we can and evaluate each of these pieces. So when you're given a problem, you need to be looking for each of these classifications. Okay, which is why I tried to organize the slides in this fashion. So we get substrate, we get nucleophiles, we get, I won't even do leaving group, and we get our solvents. Okay, the leaving group has to be a good leaving group in all cases, so I'm not too concerned about really putting a lot of weight on that. Okay, so when we look at our substrate under the SN2 conditions, okay, I'm concerned about steric hindrance, or the electron density in the backside of our leaving group bond. Okay, so that's all steric hindrance is just electrons behind the leaving group. Okay, and we just try and sound fancy when we say steric hindrance. When we move to the SN1 reaction, since I'm only concerned about that leaving group leaving, I need to form a stable carbocation. So any way I can form that stable carbocation is going to be important. Okay, and that's where some of the later rules are derived when we move into the SN1. When we look at the SN2, okay, at the strength of the nucleophile, we needed a strong nucleophile. Why? Because we're trying to push the leaving group out. The SN2 reaction forces the leaving group to leave. To do that forcing, we have to have a strong nucleophile. When we move to the SN1, because the nucleophile doesn't come into play until after the cation's formed, I don't care what the nucleophile is. As long as I have one, I can do the SN1 reaction. Both reactions need a good leaving group, like I said, so we won't worry too much about that. And unless we actually get into the alcohol chapter, our leaving groups are always going to be halides. Our leaving groups will always be halides unless we move into chapter 8 with our alcohols. Okay. Most people don't like the substrate pattern that I've listed off at the very beginning. Okay, so cation stability and steric hindrance. So we want to come up with some way that we can find an easier ranking. So we can go back and rank our substrates. This is where we get our zeroary, our primary, and our secondary for our SN2. For SN1, we only see our tertiary and secondary substrates reacting, okay, or resonance stabilized. How do you spell resonance? Sure, close enough. Okay, so when you think you've got an SN1 reaction, look for resonance stabilization. See if that's available. If it's not, then you might be pushing an SN2 reaction. And our solvent stabilities, our SN2, we want a polar aprotic solvent. I listed off a couple of those: DMSO, acetone, THF. And in SN1, we want a polar protic solvent. Any alcohol, so anything containing an OH bond, okay, is a protic solvent. OH bound to something out here, anything. Let's just say R for this point, where R could be anything: carbon, hydrogen, okay, etc. We also get a little bit of challenges when it comes to stereochemistry. And here you thought, chapter 6 would stay in chapter 6. Stereochemistry is going to show up when we look at our SN1 and SN2 reactions. Our SN2, we get inversion at the chiral carbon, so we get R going to S or S going to R. Okay, when will that happen? If you have a stereocenter. If you don't have a stereocenter, you don't have to worry about it. Okay, so being able to identify chiral carbons is going to become increasingly important when it comes to determining what products are actually formed in each of these reactions. Okay, when we move to the SN1 reaction, we can use this big fancy word, racemization, meaning we end up with an optically inactive product, okay, which means if you started with R, then you get a mixture of R, or B, roughly the same thing. If you start with R, you get a mixture of R and S products. What if you start with S? Same deal, you get a mixture of R and S for your products. Okay, so in an SN1 reaction, you'll always get two products, okay, or at least two products. So you've got to watch out for stereochemistry and make sure you account for that when you draw out your products. Okay, this last part on the rates isn't going to play a huge role. I probably won't ask any questions on it. In fact, I'll promise right now that I won't ask any questions directly on rates. That's for those of you that took second semester general chemistry, maybe it'll help tie in with why you had to take that class. Okay. Right now is when I would have you go through and do that first quiz that we went through or that I passed out on Monday. Since I can't really pause the lecture at this point, well, let's see what happens on the next slide. Hey, I actually had some questions that we could ask. So let's take a look at those questions first, and then I'll go ahead and stop recording this lecture, and I'll give you another one so that come Monday we can just work problems and kind of get you comfortable with the material before the exam on Wednesday. So if we're going to compare the following pairs according to nucleophilicity, so we could start with hydroxide. Whoops, sorry. Let's start with hydroxide. Okay. By the way, the names there are just for my sake, not for your sake. I wouldn't expect you to know the name or draw these out. So if I compare hydroxide to a carbanion, okay, in this case I'll go with a methyl carbanion. Which of these two would be the stronger nucleophile? Hydroxide, OH-, or CH3, our carbanion? Okay. Well, now is when you should go back to ranking nucleophiles, okay, which showed up earlier in this slide or in this presentation, so you can flip back to it. I'll give you a sec to find it. Okay, I'm going to assume you found it now. Our first rule is that we had to have donatable electrons. So we have to have lone pairs or pi bonds. Both of these have lone pairs, so we'll move to our next rule. Our next rule said that we had to, I already forgot, what was our next rule? Thank you, that's right, negative charge. Okay, so we look at both of these have negative charge, so we'll continue on from there. Okay, and our third rule said the lower the electronegativity, the more nucleophilic. Okay, remember that our nucleophile needs to be able to donate electrons. If it's something that's highly electronegative, it wants to hold its electrons. So it makes sense that we see this inverse. So when we compare oxygen to carbon, which one has the lower electronegativity? That's right, carbon does, which means carbon is our better nucleophile. Okay, so let's push this a little bit further. Now that we've established that carbon is our better nucleophile, because it has the donatable electrons, because it has the negative charge, and because it's lower in electronegativity, which mechanism would I predict the carbanion to react in? Would I expect it to follow an SN1 reaction or an SN2? Okay, that's where we'd go back to that previous slide and say, okay, we're looking at nucleophiles. Do I have a strong or weak nucleophile? If it's a strong nucleophile, I expect to see a negative charge. I have a negative charge, so I have a strong nucleophile. Which mechanism requires a strong nucleophile? That's right, our SN2. We would expect both of these reagents, for that matter, to go in the SN2 mechanism. Okay? Kind of makes sense with what kind of questions we can get from that. So we can go through and rank nucleophilicity and then take it a step further and decide which mechanism they'd push through. So when you see a reaction, evaluate each of those pieces and see if that narrows it down to what your possible answers could come out as. Okay? So let's try one more example here. As far as the nucleophiles go, that is. If we look at ammonia, NH3, versus iodide. Okay, according to our rules, what do we start off with? Donatable electrons. Both of these have donatable electrons. We see lone pairs on both. What's our next rule? Negative charge. Which of these has a negative charge? Iodide. Which one's the stronger nucleophile? Iodide. Okay, let's switch it up just a little bit and say, instead of me saying it was NH3 versus iodide, I said it was potassium iodide. What a jerk. I mean, why would we do that? Just to make things more difficult. Okay, Now, which of these is our strongest nucleophile? Okay, a little bit trickier. They both have lone pairs, and that negative charge isn't obvious, except what is special about that bond between the potassium and the iodine? Okay, well, potassium is a metal, iodine is a nonmetal, which means that bond is ionic, which means when I see potassium iodide, it's not really potassium iodide, it's K plus and I minus. The negative charge is still present. Iodide is still going to be our better nucleophile. Okay? So sometimes that information will get hidden from you. Be aware of that. Always watch out for that ionic bond. Okay? Let's go ahead and look at leaving group ability. Okay? Water versus ammonia. Okay, this could be a fun one depending on how much information you already knew. Okay, so our leaving group needs to be able to stabilize the electrons that it takes from our substrate. So I'll go ahead and show the electrons that were removed from our substrate in red. So in this case, oxygen took the bond between it and the substrate. Does that show up? I think that shows up. And formed a lone pair. Same thing on the nitrogen. Okay. So our leaving group needs to be able to stabilize the electrons that it takes. Typically, we'd see that as a negative charge. This case, we don't see the negative charge because our leaving group stabilized that negative charge, ultimately making it neutral. Okay. So which of these two lone pairs is the most stable? Okay. Also said, which of these two lone pairs is less reactive? Okay. Said another way, which one of these lone pairs would be, that's not quite said another way, which of these lone pairs would we expect to be most willing to react with something else? Okay, so now what we're looking at is the negative. Okay. Well, what's the difference between an oxygen and a nitrogen? There's no size difference. We could now move to electronegativity. Which one's more electronegative? Oxygen's more electronegative, which means it wants to hold its electrons tighter than nitrogen. Which one ends up being the better leaving group? Which one would rather hold those electrons? Hopefully we got water there. Okay, and water will act as our better leaving group because it's more stable. Okay, so we can relate this back to base strength. Okay, water is the weaker base of these two. Okay, so let's try another one here. Could do chloride versus iodide. Okay, so we got our chloride and we have our iodide. Okay, between those two, which one's the better leaving group? Okay, again, what we're trying to do is see which one can hold those electrons better. Okay, our first rule of thumb on trying to determine electron reactivity is size. Okay, the bigger it is, the charge is distributed over a larger area, meaning it's effectively a smaller charge. When we evaluate these two, iodide has it spread over a much larger area. Iodide is the better leaving group. Okay. Very last one that we'll go through and compare. Okay, we got hydroxide, whoops. We've got hydroxide, our negative charge, versus sulfate. I'm probably going to run out of space on this. Let's see what I can do with it. Versus our sulfate anion. So this one's going to be kind of tricky, maybe kind of not. Okay, let me highlight our reactive electrons. Okay, so these were the electrons that we're trying to ultimately stabilize. Okay, so in both these cases we've generated negative charge. Okay, as a leaving group, that's not the greatest thing, but if we can stabilize it through size or perhaps electronegativity, maybe we can get it to work out. Okay, so we'll look at the base strength of each of these. Okay, well, let's look at the base strength first. Hydroxide, is that a strong base? Hopefully you remember your definitions from Gen Chem. Sodium hydroxide, calcium hydroxide, anything with hydroxide is a strong base. So we got a bit of a problem here. Hydroxide's a terrible leaving group because it's a strong base. If we move over to the sulfate, okay, that one might be a little bit trickier to evaluate because it looks like we have two negative charges. We might say, oh, that's pretty bad. Except what happens when we add hydrogens to our sulfate? We form H2SO4. What do you know about H2SO4? Strong acid. By definition, the strong acid completely dissociates into the ions. So what are the odds that that negative charge is going to be very reactive? Slim to none, which means our sulfate is more stable as that negative charge, which then means sulfate is our better leaving group. Okay? So there's another way that we can evaluate that, because perhaps you don't remember your acid-base definitions, is we want to see if we can stabilize that negative charge somehow. Okay, so when we compare these two, oxygen to oxygen, no difference. So another way to stabilize is to try and do resonance. We push these electrons towards the hydrogen, in the case of hydroxide. Can I stabilize it? Can that hydrogen accept more electrons? Okay, good answer, no, it can't. So we push the electrons right back, no result. Okay, so no resonance stabilization. What happens in the case of sulfate? Whoops, dang it. Wasn't supposed to be an eraser, so let me redraw that real quickly. So negative. Okay, so what we're going to do is move that lone pair towards a bond. Okay, we've now exceeded the octet for sulfur, so we want to bust a bond. Okay, we need to break a pi bond if we're going to do resonance. Do we have a choice of pi bonds? Yes. Which means I can do resonance. What does resonance do to reactivity? It decreases reactivity, so we get lower reactivity, which means it's a weaker base, which then means it's a better, that's not supposed to be a letter leaving group, it is a better leaving group, or just LG. Okay, so all these different options, all these different thought processes on how you should be going through each of these. Okay, you'll notice one of the questions that I didn't ask for any of those leaving group ability pairs was which mechanism. Okay, why not? The leaving group was ultimately the same in all mechanisms, or the SN1 and the SN2. We needed a good leaving group, period. It didn't really matter beyond that. Okay, so we can't tell our mechanism based on the leaving group. Okay. Last kind of thing that we can evaluate, I'm not going to start with bromobenzene, but we can go through and look at a substrate. Okay. What kind of alkyl halide do I have here? So to evaluate, what we'll do, look where our chlorine is attached. We'll take a look at that carbon and evaluate what things are attached to it. 2 hydrogens and 1 carbon. This is a primary alkyl halide. Which mechanism wanted the primary? SN is a good place to start, and we would end that with the SN2. We want the smallest backside attack. Okay. The primary also doesn't form a stable carbocation, so we can't get the SN1. Okay. What happens if instead I had, oops, let's go with a different color again, go back to our blue. this was my substrate. So 2-chloropropane. Okay. Again, we want to classify our carbon where our chlorine is attached. We've got that carbon. It's bound to 2 carbons and a hydrogen, so we're looking at a secondary substrate. Which mechanism preferred the secondary substrate? Bit of a trick question. Both preferred that secondary substrate. So if you looked at just the substrate, we would expect both the SN1 and the SN2 reactions to occur with this substrate. Okay, both are possibles. Okay, so let's try 2 more options here. What if we had something along these lines? Okay, you know what? Let's make it really confusing. Let's add, you know, a nice fancy benzene out there. Okay, hey, why not? Let's throw in a nitrogen. Holy crap, that's confusing. What should we do when we look at this problem? Well, what chemistry are we studying? We're studying the alkyl chlorides. That's where our reactivity is. The rest of the structure is there only to confuse you, so ignore it. We'll evaluate the carbon to which the chlorine is attached. It's got 1, 2, 3 carbons attached to it. It is a tertiary alkyl halide. Which mechanism would we expect? SN1. Okay. So don't get bogged down in the bulk of the structure. Look only for where you know chemistry to occur. And at this point, we're only concerned about the alkyl halides, which means ignore everything else. Focus just at that point. Okay. Yes, it's going to get more complicated than that, but we'll cross that bridge when we get to it. Last substrate I want to throw at you. This is the one that's actually named there, bromobenzene. Okay. This one's a bit tricky. As we look where our halide's attached, we got that carbon, but it's not an sp3 type carbon, which means we can't rank it based on primary, secondary, tertiary. We have to come up with a different nomenclature system. Okay, that system is going to come based on that bond. Okay, that carbon is sp2 hybridized. Okay, so we'll refer to its reactivity based on it being sp2. Okay, so let's look at our 2 mechanisms. We had the SN1 or the SN2 mechanism. So let's write SN2 over here. We'll start with that one. SN2 was backside attack, so it's got to come in, our nucleophile has to come in from that to kick out our leaving group. Okay, well, what does this double bond represent? Or this one, or this one? It's all electrons. What was our nucleophile? Nucleophile was a big ball of electrons. What are the odds I'm going to be able to jam that nucleophile, that negative charge, in near a whole bunch of other negative charge? Good call. Not very likely. Which means what about the reactivity of an sp2 carbon in an SN2 mechanism? It's not going to go. We don't see the SN2 mechanism occur with this kind of position. The next option is looking at an SN1. Okay, and we said we needed a stable carbocation. Okay, this one's a lot ran out of space. A lot harder to evaluate. We could go ahead and look at what happens when that bromide leaves. Okay, and put the positive charge there. We do not get resonance. Okay, it's a perpendicular orbital argument. Okay, that carbon is now sp hybridized. The p orbital from our carbocation and the p orbital from the double bonds, perpendicular positions, can't overlap. Okay. So we don't get a resonance stabilization. Well, maybe we get a pseudo stabilization because there's 2 carbons. Okay. Well, let's go through and evaluate the bond angle that would have to be around that. That's an sp carbon, so it has to be 180 degrees. So we would have to do something along these lines to get that structure. Okay, that means the bond angle for this double bond would have to be 90 degrees. Okay, where it wants to be 120. It's too much of a bond angle crunch, not going to happen. Okay, what does that mean? this carbocation can't form. Well, if the carbocation can't form, what happens with our SN1 mechanism? Good call. Can't do the SN1 either. So what mechanism, or what substitution mechanism, do I get with bromobenzene as the substrate? I don't get one. There is no substitution. The reaction does not proceed. Okay? So it's kind of a trick question. You can expect to see that on the exam, so kind of watch out for that. Okay? I would recommend at this point that you go through and work the quiz if you haven't done the quiz already. I will go through and post the next lecture in a little bit, or I'll complete the next lecture and then post another quiz where we're adding information about the elimination reactions and maybe a little bit on alcohol reactivity. We'll see how long I can talk to myself. Okay? If you've got questions, feel free to send me an email, and I will talk to you soon.